Hi all, thanks for attending our session. I would like to first thanks IAAI 2021 community um, and chair for giving us an opportunity to present our work on an end-to-end solution for named entity recognition in e-commerce search at the Home Depot. Let me introduce you to my team at the Home Depot who worked on this project from data science and machine learning engineering side. Priyanka Goel, Mitchell Bowden, Sean Cheng, Faizan Javed, Thomas Packer, and myself, Bhushan Ramesh Bhange. I currently work at the Home Depot to solve various business problems with help of data science and machine learning engineering. So this is our today's agenda for this session, starting from introduction to named entity recognition problem, the literature overview on NER, and industry application challenges we still have despite of all of this recent research work has been done, and our approach starting from data preparation, training the model, and productionalizing the model. I will also talk about some of the model experiments that we did, selecting the model architecture, on selecting custom word embeddings, some more experiments on maintenance side. After that, I will talk about results, what business impact this model did for Home Depot search. Along with that, I will continue to talk about the future work and conclusion, and we'll take the questions. All right, so let's get started. Named entity recognition is a common information retrieval task to locate, segment, and categorize predefined set of entities from unstructured text. Just to exemplify, LG washer mini. This is one of the search query wherein LG is a brand, washer is a product. So NER will give the output as shown on the screen, as a brand as LG, product as washer. And since we use BIO schema, so in this project, so which means beginning of the brand, inside of the brand, beginning of the product, inside of the product, and other. So one of the fundamental challenge in our search engine is to understand a search query and extract entities, which is critical to retrieve the most relevant products. In case of Home Depot, those are brand, product type, color, size, etc. So NER is not new. Since 1990, this has been extensively studied and evolving rapidly every single day. It is exciting to see this booming progress based on the deep learning models and language models. At first, this problem seems very trivial and can be solved by keeping a dictionary of entities, like in case of Home Depot, keeping a unique brands dictionary and unique product types dictionary. And that's what exactly we started with as in our baseline production legacy NER, which used to do sequential greedy exact match, starting with brands and then matching product types with the longest match will be selected as an entity. But as we go deep dive in this, we see there are a lot of challenges. Some of those are search queries having multiple product types but only one shopping product type. As an example, if you can see fridge, no ice maker, there are two product types in this. One fridge, another entity is ice maker, which is also a product type. But there is only one shopping product type, as we can see, it's a fridge. Then there are other problem wherein brand name and product type both are same, creating an ambiguity. Example, weed eater lightweight, wherein weed eater is a brand and also a product type. There is another problem wherein new product type itself are not available in predefined taxonomy. And hence the mislabels often closely relate to the context in the query and specific entity values. And hence it is kind of difficult to fix at scale in the legacy NER system, even with help of synonyms and all sort of dictionaries. And hence deep learning models along with language model, word embeddings are good candidates to handle this kind of complexities. So let's talk about the literature that we have so far on the NER starting from 2011 to 2019. As you can see, there has been a lot of research starting from using CRF, with feature based, then CRF with deep learning, CRF with custom word embeddings, and so on and so forth. So, in summary, there are these three papers in 2017, 18, and 19 which explore deep learning for NER in e-commerce search. Two papers talk about production evaluation and queries, and another four papers talk about leveraging the large number of unlabeled queries available to commercial search engines. It's exciting to see the research progress on deep learning methods and language models, but relatively few publications explore its application in industrial settings. And that's a gap between academic research and industrial applications of NER. Focused outcome often is marginal improvement of F1 scores and no consideration of feasibility in real world applications. And hence, we feel industrial applications being left behind due to the unique challenges. So, what are those industrial application challenges? Deep learning method with word embedding language model is a way to go forward, is our recent research has shown us. But it is challenging to start to build a training data set and custom word embeddings from the scratch. Industrial applications often require custom domain specific knowledge and training data, covering the full extent of entities of different types, noisy intent signals, etc. Machine learning models, especially deep learning models, usually require large amount of high quality training data, which is often time consuming and sometimes impossible to acquire. And the next challenging productionalization of these deep learning models, which is computationally expensive to train and doing real time serving of this model. To address these challenges, our paper demonstrates an end to end solution starting from data preparation, training the model with triple learn framework, and then production deployment details of real time usage in our e-commerce search engine. So let's talk about our approach at Home Depot that we took for solving this NER problem. So let's get straight. So we definitely need large volume to train, high quality labels to provide correct supervision, and then high coverage of label values to potentially recognize all of the entities. But we need to admit that it is time consuming to prepare one set of such training data, and hence we propose a novel approach, triple learn, so which may resemble a natural way of learning. So let me give you an example or analogy wherein a person is trying to learn a new language, as you can see in the figure. There are three types of sources generally one refer. One's textbook, which is high quality content having exercise and their solutions, which is kind of a golden data, isn't it? Then we have dictionary, wherein it tries to cover most of the words, vocabulary, and common phrases, which is analogous to the catalog of, let's say, in Home Depot, all the unique brands and all unique product types. Then variety of real world materials such as TV shows, movies, medium articles, blogs. So those may be noisy, but they have a lot of patterns in it, which is required to learn a language. So learning a language is also an iterative process, as I just discussed. Learning from each type of the material in each iteration. Validate the learning using high quality textbook contents and its exercises. So we keep going through this process iteratively so that we can learn from vocabulary, more complex patterns, which is similar to how our triple learn works. So here is an end-to-end solution with triple learn framework highlighted in bold and orange. The phase one prepares three sets of training data for triple learn. One is large noisy training data, another is synthetic training data, and third is golden training data, which we are going to discuss in more detail. Second phase is iterative training process of triple learn, and then the last phase is the model productionization. So let's talk about the training data preparation, which is phase one. So we are considering two fundamental sources which are commonly available in most of the industries. One is product catalog data. So all the products sold on homedepot.com, such as 14K unique brands and 11K plus unique product types. And another data source we're talking about is customer behavior data, which stores customer shopping journeys, including searches, impressions, clicks, and purchases. So before we go further, I would like to give more information about one vocabulary, which is entity sequence pattern. So what does that mean? So let's see as an example, Milwaukee Chip Drill. So Milwaukee is the brand, then chip is other, and then drill is a product. So it got a sequence pattern of brand, other, product, and so on and so forth. So our model is sensitive to this order of entities in the training data, which makes sense for a sequence tagging model. So let's talk about the training data sources. First, we create the raw training data using rule-based algorithms by matching the tokens in product catalog and customer behavior data. This comes around 2.7 million queries. Um, it's noisy, but it still captures the variety of patterns in real-time customer search queries. Then we use rule-based algorithm to build synthetic data using all the brands and products in our product catalog. So we can form queries synthetically like brand only queries or product type only queries. So that's how the pattern would be, which will include all the distinct brands and products to let model potentially recognize them all. Since model is sensitive to the order of entities in the training data, golden data is vital to start the model training in triple learn to measure the real model performance. So from these two data set, we draw 16K samples based on entity sequence patterns, which I just discussed earlier, to avoid the bias and overfitting. And it is a minimal effort to annotate these 16K examples with help of human. So that's how we form three data sets. So one is synthetic data, which we form from product catalog, just brand only queries, product only queries, brand product queries. Large noisy training data, which is formed from customer behavior data with help of catalog, and golden human annotated data, which are around 16K, which is the input to the next step, which is triple learn. So the golden training data is around 16K. We took 15% of that for testing. And rest of training data is 90% and 10% is taken for validation. And after that, before training, we do data pre-processing to balance the labels of ambiguous entities in order to avoid the bias generated due to skewed data distribution. Then model training happens, and we record the F1 score of that model. Also, we do evaluation on the held out data set. Once model is trained, the next step is, remember, we have those large noisy training data still remaining and synthetic training data. We sample those similarly as we did in the first step by sampling based on the entity sequence patterns. We again pass those through the newly trained model, try to get the positive examples, and then trying to add and trying to formulate additional training data, doing all the sampling work, then again doing all the pre-processing, then doing the model training once again, and evaluating the model, recording the F1 score. So this will continue till our F1 score drops from the previous iterations or we exhaust from our training data sets. The core of our solution is novel model training framework, Triple Learn, which iteratively learns from these three separate training data set instead of one training set as traditionally done. As you can see in the figure, the iteration 1 starts with training examples like 14K. At the first iteration itself, we saw the significant improvement of 88.82. And after that, we continue with this iteration of learning. At one point, as you can see in iteration 7, we see F1 score of 93.30, which is good, and hence, and after that, it did not improve. So we chose the iteration 7 model for production. As you can see in the next figure, we did a baseline with respect to legacy NER system, which is at 69.5, the red line. If we take all the training data in one go and try to train again the same model, in the first iteration we see we get a result of around 87. But if we use triple learn approach, as you can see in the green line, we see improvement iteration by iteration. So the collaborative supervision is what triple learn leverages using these three separate data sets. Golden data is a ground truth to start the model training and to measure the real world performance. Large noisy data provides rich variations of real world patterns. Synthetic data fits the model all possible entity values which may or may not show up in the golden data or the large noisy data. And next step is productionalization, which is phase 3. So once the best model is selected, the next step is to productionalize it to make a real world impact. But there are challenges. One is a speed and another is a cost. So we need to serve thousands of search queries per second and help retrieve search results within SLA response time. Speed has a direct impact on user conversion rate and satisfaction. Second is cost. We need to justify the return on investment by lowering the serving cost of the model. So there are some solutions we used. So we used an TensorFlow serving with gRPC Java client. And the optimized model has significantly in smaller size. It shows faster loading and faster inference. So we reduce the model size by freezing the variables into constants, stripping out unreachable parts of the graph, folding constant, doing batch normalization, removing training and debug operations. We did use TensorFlow serving for hot swap model deployment and AB feature without zero downtime. We managed to use custom TensorFlow serving, also custom machine type with scalable deployment on CPU in the GCP VM. This has proven to be a cost-effective solution for us, giving 26 millisecond for 99% of response time under the 5 times heavy load that we get during the traffic we get during the holiday peak. This is very satisfactory for our search engine. Now I'd like to talk about the model experiments. So before we go that, the model architecture that we use, which is inspired from the recent research work done in the NER, the one that we use is bidirectional gated recurrent neural network with help of CRF layer. So in this, the character embedding we use was generated from bidirectional LSTM RNN, and the last layer used was the CRF. The model architecture experiments, as you can see, we tested it against 6. The bidirectional LSTM, bidirectional GRU with CRF, without CRF, with character embedding, without character embedding, and also we try to experiment with transformer-based BERT, uncased large, pre-trained one. But as you can see in the figure, we see the good performance for BiGRU CRF with character embedding. And for word embedding, we have experimented with pre-trained one, pre-trained Glow, pre-trained word2vec, and we also built our custom word embedding trained on 50 million search queries and 3 million product titles on homedepot.com. Word embedding had simplified feature engineering for us. It had given semantic representation using domain-specific word embedding. It has shown maximum vocabulary coverage, better model performance. The table shows the top 3 similar words for Milwaukee, which is city, but also a popular brand in the home improvement domain. So as you can see in the table, similar words in pre-trained Glow, it shows Chicago, Detroit, Minneapolis, and which is correct. Same as for word2vec pre-trained. But in terms of this domain specific, we see if we use custom word2vec, we see Dwalt, Makita, Rigid. These are the brands which are similar to Milwaukee, and we see vocabulary coverage using custom word2vec is 99.9, and that's why it relates to giving the better model performance. Now let's talk about the maintenance. There is no model that works well forever. It's especially true in e-commerce scenario wherein the model drift, whenever there is a model drift, it needs to be refreshed. Some of the experiments that we did on this model is improve the performance on short queries, which are more average traffic than long queries. So for this experiment, we just have to add 5% additional short queries training data to our golden training data set to retrain the model. thanks to triple learn framework pipeline. That's why we do not have to put a lot of effort. Similarly, for the model, we retrain the model to cover new brands and new product types, which we recently added to our product catalog. We just built a new synthetic data using this and updated that synthetic data training data set, and some of the small amount of data we added to the golden data set, and the model was retrained, and it is a minimal effort. It is easy to refresh the model because we only need to incrementally update a small fraction of these three data sets to retrain the model, again thanks to triple learn framework pipeline. And the most important part is results. Offline test showed significant increase in F1 score, 69.5 to 93 with compared to legacy NER system. We did an A/B test online, wherein with millions of search visits from real online shoppers shows significant improvement in both click-through rate and revenue conversion per search. Estimated annual business impact is $60 million in incremental value. We also use this input for as an additional input for our ranking. The cost of maintaining this is minimal, and hence it is yielding high return on investment. This has replaced the legacy NER and has been live on Home Depot since more than 9 months, I guess, serving millions of real customers and boosting search conversions. Also, this has given us a reusable triple learn framework pipeline for other ML work too. Now, moving to future work and conclusions, we have a plan to include more named entities such as color and size, enrich knowledge graph by extracting entities from product description, title, etc. for our offline applications, and testing this framework using publicly available datasets for easier reproducibility. And I would like to conclude this presentation by saying our core solution is this novel model training framework triple learn, which is analogous to reverse bootstrapping but not exactly same as that. This learns from 3 separate training datasets instead of 1 training dataset as in traditionally done. This novel framework works with less satisfactory training data. In most industrial settings, it is often too expensive to prepare large amount of high quality data, but the noisy data and catalog data or dictionary based data is readily available. This is easy to maintain, refresh the model by just incrementally updating one or other data set based on the need. As for THD, it has shown the significant improvement in offline tests, increasing the F1 score. Also, in the A/B test, we have seen the significant improvement in user engagement and revenue conversion. The model has been live in the Home Depot since last 9 months, as I discussed, which is boosting the search conversations and revenue. Beyond our applications, this triple learn framework, as well as the end-to-end process, is model independent and problem independent. So it can be generalized to more industrial applications, especially to the e-commerce industry, which has similar data foundations and problems as discussed in details with the details in this paper. And finally, I would like to go for questions.